Welcome back, ladies and gentlemen, to another exciting episode of Dave Does Math from Home. In this section, we're talking about 2.2. This is more on functions. I want to say a very brief word about section 2.1, which you may have watched just before this. That video for 2.1 was recorded about a year before this one was. That was sort of before I had a good place to do recordings, before I had a nicer camera, and before I'd figured out lighting. So if that video is terrible and really unfortunate looking and is very hard to watch or does not explain things very clearly, please let me know. I would be very happy to re-record it. If it is adequate, then good. I hope you enjoyed it. This video is not really going to pick up where we left off a year ago with that other video. But we're going to talk about functions. The other video should have covered all of the things that are like very basic about functions, like how to evaluate functions of things. I like to just rewrite the function with a bunch of empty sets of parentheses, then put things in the parentheses and just do standard issue, normal, regular math on those things. So we're evaluating functions, we're learning what functions are, which kinds of equations are and aren't functions. For us, the definition that we're going to go with and use is that functions need to be equations with at least two variables, x and y. One of them should be an input and one of them should be an output. And we should also have the condition that each input is associated with exactly one output, so that we don't have this weird situation happening where one input will give us two possible outputs. That's no good. So that's what a function is. We did evaluating functions. We talked a little bit about graphing. You can always, if you're going to graph a function, you can always just make a table of values and then plug in those numbers. Put those numbers on a graph, those points on a graph. That's 2.1. So that's a review in case the last video was terrible. In section 2.2, there's 3 additional things about functions that we need to talk about. The 3 things that we need to talk about functions in 2.2 are: we need to talk about increasing and decreasing on intervals, we need to talk about piecewise functions, and we need to talk about difference quotients, which are all very important. And we're going to start with increasing, decreasing. If we have a function, increasing and decreasing is largely a graphical thing. So we're not going to be playing around much with function equations here. We will revisit the idea of increasing and decreasing functions starting from equations instead of graphs when we get to calculus. That's actually an enormous part of what Calculus 1 is about. If you don't have a graph, if all you have is the equation of a function, and you want to find out exactly where it's increasing and exactly where it's decreasing, calculus can help us with that. For now, we're just going to talk about increasing and decreasing graphically. And we'll start with a pretty simple looking function. If you have something like this, this is a parabola that has been shifted to the right a few units. It hits here. If this is, let's say that's 3. 1, 2, 3 on the x. It's sort of tempting to say that the function is always increasing, because like if you start from here and go to the left, it's increasing, and if you start here and go right, it's increasing, and if you start here and go left, it's increasing. But that's not what increasing means. Like, it's also tempting to say it's increasing because you get arrows pointing up in both directions. So it's tempting to say that this thing is increasing everywhere. But that's not what increasing means. Increasing means as x moves from left to right. So x is always moving in this direction. As x moves from left to right, are your y values increasing or decreasing? That is what increasing and decreasing means. You're talking about increasing or decreasing y values as x goes this way. So actually, for this half of the function, things are decreasing. As x is moving in this direction, my y values are decreasing on the interval negative infinity, that doesn't get a bracket, that gets a parentheses. On the interval from negative infinity to 3, everything's going downward. And it is increasing on the interval from 3 to infinity. So one of the challenging parts of this section, when we first introduced this, and maybe you've been introduced to this before and I don't need to talk about it much, but I'm going to talk about it just in case you haven't been introduced to this. This way of writing things is called interval notation. And it's really sort of unfortunate because when you write things in interval notation, it looks like you're writing a point. Like if you just see 2, 5 in parentheses, this looks like it should be the point 2, 5. 1, 2, 1, 2, 3, 4, 5. It looks like you got this point here. And it could mean that, or it could mean 1, 2, 3, 4, 5. It could mean this interval from 2 to 5 on the x-axis. So the notation here is pretty unfortunate, but we're going to have to deal with it. Interval notation uses a starting point and an ending point in parentheses to describe intervals. Sometimes, in this section, we're not going to see this, but sometimes you'll see interval notation that looks like it will have a hard bracket on one side or both sides, perhaps. 3 to 10. Sometimes you'll get hard brackets on both sides instead of parentheses. The difference between hard brackets and parentheses is the difference between inequalities and strict inequalities. So this interval here, 4, 7, this means that x is greater than or equal to 4, but strictly less than 7. That's the hard bracket is less than or equal to. The parentheses is strictly less than. On this one, you could say that 3 is less than or equal to x is less than or equal to 10. Because if they're both hard brackets, then they're both less than or equal to, less than or equal to. For this one, if they're both parentheses, then it's 2 is strictly less than x, which is strictly less than 5. So this is a way of writing these sort of boundaries or these intervals in a way that I guess it does save a little bit of time, but it's still sort of unfortunate that it looks so much like a point. And yeah, if something doesn't have a bound on one side or the other, you'll just say that it goes to infinity. So that's interval notation. That's the basics of increasing and decreasing. Let me do another thing that looks a little bit like that, and then we'll talk about piecewise functions. So let's consider a graph that looks like this. We'll say that's 2, and then it goes flat, and then it curves down like a parabola. 3, 4, 5, 6, 7. So if we have a graph like this and we're being asked to determine where it's increasing, where it's decreasing, again, it's sort of tempting to say that it's decreasing everywhere because both of these arrows are pointing down, but we're not. Don't pay attention to where the arrows are pointing. That is like a red herring. That is not what we want to look at. That is not what determines increasing or decreasing. Increasing and decreasing is all about what the y values are doing as x moves to the right from the left. So here, as x moves from the right, our y values are increasing. So that's going to happen from negative infinity to 2. Between 2 and 5, the function is constant. If your function is just a straight, flat, horizontal line, then it's constant from 2 to 5, and after 5, it is decreasing. So we'll say that from 5 to infinity. So, interval notation, being careful about increasing and decreasing, meaning things happening from left to right. The other important thing that I want to note about these specific kinds of problems is whenever a question asks where something is happening, if a question is asking where is it increasing, or where does it reach its maximum, or where is it constant, any of these where questions about functions are always referring to x values. So I see a lot of students trying to answer these questions in terms of like x and y. Like, I don't know, maybe if this is the point 2, 2, they'll tell me something about increasing until 2, 2. I want to say this because the y values don't matter. They don't matter at all, even a little bit. All of these where questions, they're exclusively about x values. X's are where things happen. Y values are just what's happening. So anytime a question is asking where something happens, all they want is x values. These are intervals of x values. Y is not a part of this. So that's increasing and decreasing. Let's talk about piecewise functions. I should not have erased that so swiftly. Some of you may have been looking at that shape that I just erased and thinking, Dave, that function looks impossible. It looks like a straight line for a while, and then it looks like a horizontal line for a while, and then it looks like a parabola. No function does that. And I'm here to say, yes, some functions do that. And the way we get functions to do that is by creating something called piecewise functions. Piecewise functions, when written analytically, look a little something like this. F of x equals, let's say, 2x minus 7 when x is less than 4, and so when x equals 4, that'll be 1. So we'll just say x, or 5 minus x. That'll work. 5 minus x when x is greater than 4. So this is called a piecewise function, and it's giving you two different rules. And it doesn't have to be two. Some piecewise functions have 3 or 4 or 5 or whatever. But it's giving you different rules on different parts of the domain. So if we're going to try and draw this, if we're going to see what this function looks like or evaluate it somewhere, this is the rule that the function is going to follow until x equals 4. So on this is sort of the dividing point. X equals 4 is where it switches from one rule to the other. So everything to the left of this is going to use this rule, 2x minus 7. So 1, 2, 3, 4, 5, 6, 7 to 5 to 3 to 1 to 1. Everything to the left of this line, it's doing this. To the right of this line, it is doing 5 minus x, which I think is kind of like this. So this 5 minus x would have an intercept of 5 and a slope of -1, but it doesn't actually have an intercept of 5 because it's not defined back here where the intercepts happen. So this is a piecewise function. To the left half, it uses this rule, which is a line with a slope of 2. On the right half, it uses this other rule, which is a different line with a slope of -1. And these functions can have, I mean, they don't have to be linear. You can put any function pieces you want here and whatever bounds you want here. as long as it still passes the vertical line test. One of the problems with piecewise functions is getting overlapping pieces of the domain. These pieces of the domain cannot overlap. They have to be perfectly distinct. So in this one, we sort of set it up so that these two would meet at that point, right at the boundary line. They both have the same value. So if you plug in x equals 4 here, you get 8 minus 7 is 1. And if you plug in x equals 4 here, you get 5 minus 4 is 1. They don't have to do that. If you wanted this to be something like 8 minus x, then this line would just be shifted up 3 more units. When that happens, one of these sides gets a filled in dot and the other side gets an empty circle. And you determine which is which by which of these gets the strict inequality and which of them has the less than or equal to inequality. So because when x equals 4, we're going to use this rule instead of this rule. That means that this one gets the shaded in dot, because that's what happens when x equals 4. And this gets a hollow dot, because that's what happens at everything really, really infinitely close to 4. Like 4.000001, that uses this one. You could throw in a few more zeros in there before that 1, you're still using this guy. So that's piecewise functions. I don't think any of the problems on the homework are asking you to graph them like we just did. I just wanted to give you a sense of what they look like when graphed. The homework questions that you're going to get are going to be more like, here's a piecewise function, f of x equals 5x squared minus 20 for x is less than or equal to 2, and 3x plus 17 for x for 2 is less than x is less than 5, and we'll say negative x cubed for x is greater than 5. So you'll get some crazy piecewise functions that look like this, but then you're not going to be asked to graph them because that's kind of a lot. You will be asked to evaluate them. So problems will ask you like, what is f of 8? And you'll have to figure out which of these 3 rules to use depending on what the input is. So if you're asking about 8, 8 is not less than or equal to 2. It's not between 2 and 5. It is bigger than 5. So we're going to have to use this one, the negative x cubed. So f of 8 in this case is negative 8 cubed, because we're using the bottom rule, which is negative 512, I think. Sounds right. If something asks for f of 2, we need to figure out which rule to use. This one looks tempting because I see the 2, but this is a strict inequality. So I can't use this, I have to actually use this one. If x equals 2, I'm using this guy. And that'll be 5 times, so this will be 5 times 2 squared minus 20, which is I think 0. That works out nice. And if something asks for, say, like f of 4, then we'll use the middle rule. It's going to be 3 times 4 plus 17. And that'll give us something like 29. So this is how we evaluate piecewise functions. Figure out which piece of your domain your x value lives in, and then use the appropriate function for that thing. You can get your values. It's not so bad. That's going to do it for this video, but stay tuned. We still need to talk about the third part of this section is difference quotients, which are kind of a doozy. So you'll want to tune in for that.